Hello everyone and welcome to my channel. If you want to know how to analyze a binary by emulation using Qiling Framework, which is based on Unicorn Engine, then do watch this video. For those who don't actually know, Qiling is an advanced binary emulation framework which supports many different platforms and architectures such as Intel x86 64, ARM64, MAPS, and many more. It uses a well-known Unicorn engine. So if you have ever used Unicorn engine for emulation, or if you are following this playlist where I have posted videos about how to use Unicorn engine, you would have known that Unicorn is not aware about the operating system and its environment. So we have to manually load the binary and create memory segments. That's where Qiling Framework comes into the picture. One of the main advantages of using Qiling Framework is that it understands the operating system, which means that it knows how to load libraries and executables, how to relocate shared libraries, how to handle syscalls and other handlers. So you don't have to bother about how to load the binary and how to handle external symbols and dependencies. Also, don't forget to like, share, and subscribe to get the latest notifications whenever I upload more such videos. So currently we are here at the Qiling Framework GitHub page and it's open source and you can install it either using this Docker file or via pip3 install Qiling command. Now in order to learn Qiling Framework, we have this Shielder QilingLab challenges. Now in order to learn Qiling Framework, we are going to solve this QilingLab challenge which they have developed with the aim of learning. Here you can see that in total they have 11 challenges and you can download the binaries from here. So they have provided binaries for x86-64 architecture as well as for ARC64. So whichever architecture you are comfortable with, you can download the binaries and start emulating. I have already downloaded the binary here and now let's try to execute it and see how it looks like in action. Okay, so now let's fire up our terminal and change our current directory to our working directory, which is present at documents, training, and then there I have this QilingLab, and here we have this binary present. Now, if you see, this is the ELF binary for ARM ARC64 version. You might have already know that by using QEMU ARC64 static we can actually run this ARM64 based binaries on our Intel machines and I just need to tell it from where to load the loader, so it's there at this place and then we can provide our binary and it's executed and you can see it is showing the challenges. So in total 11 challenges are there and then it has a checking function where it tells us how many challenges we have solved. Okay, so let's start writing our emulation script now using Qiling Framework and along the way we will learn about different Qiling APIs. Alright, so first I'm going to open my Visual Studio and I'm going to create a file, let's say emulate.py. The first thing which we need to import is the Qiling framework itself. So for that we can simply write from Qiling import Qiling. So now our Qiling framework has been imported. Then we are going to initialize Qiling object. Before that I would like to show you a very interesting documentation which is this Qiling framework documentation, and basically it will tell you how to use the Qiling framework and all of its APIs. And it's actually very well written and explained. They have even categorized the APIs in different sections, so it would be easy to look for certain things. So, for example, if you are looking for some API related to hooking, then you can go to this hooks section and then it will show you about the hooking API along with the example. Then we are going to initialize our killing object, and this will take two arguments. First one is the binary itself, and second one is the root file system which contains the ARM64 Linux libraries. Qiling Framework already has root file system available for most of the architectures and platforms. So if we go back again to the GitHub page and over here under examples, we have this root fs directory. And if you go here, there you can see all the root file system for different platforms are present, and you can download the one in which you are interested in, or you can clone this whole directory and pass it as the second argument so that Qiling Framework will know from where to pick the libraries. Now I have already downloaded it and it's there in my documents under Qiling underscore root fs. So I have downloaded all of them, but for this binary we need ARM64 underscore Linux one. So what we are going to do, we are going to initialize this by passing the binary name as first argument, right? And then as second argument, we need to pass the path of our rootfs directory, which in my case is present at home kali documents killing underscore rootfs arm64 underscore linux, right? Then we can simply start emulation by typing ql.run. So our basic script for emulation is ready, I guess, and let's try to run it. Python 3 emulate.py. Target binary not found. I guess I have mistyped the name of our binary. Let's fix this. All right. So this first argument we need to pass it in an array form because it takes multiple arguments. So this is argv. So in case you have runtime arguments which this binary take, you can pass it as comma separated values. Okay, so I hope this will work now. Okay, yes. So we have something executed. Okay, so one thing by default, Qiling Framework shows you the output of all the APIs which are being called along the way, and it basically looks similar to what strace gives us. So if you don't want this output, you can simply disable it by passing a third argument here, which is verbosity. So you can set the verbosity level here. By default, it's default, but for now, I am just going to turn it off. And this QL verbose is actually part of another module, which is from Qiling constants import QL verbosity. Okay, so let's clear the terminal, and if we run the script again, okay. And now we can see our challenge descriptions, and then it's checking for whether the challenges have been solved or not. Okay, and it is showing us this error. So the binary is crashing at some point, and here you can see the memory map, whatever has been loaded in memory and what is the memory structure. So that's the way how Qiling Framework shows you the backtrace whenever any exception or error has been generated in the script, right? And you can see it is saying that it's invalid memory read. Over here, if you see under program counter register, it's throwing error from this offset. So that's how you can utilize this crash output in order to figure out exactly the origin from where the crash is being occurred. So let's see our first challenge description is store 1337 at pointer 0x1337. Also, we need to disassemble the binary and analyze it statically. And for that, I am going to use Radare. Radare is a very famous open source disassembler and it's really powerful. So I think this is a good opportunity if you are not familiar with Radare to see how we can actually use Radare for disassembly purpose. Fire up Radare and pass our binary. So now Radare has loaded the binary, but we need to tell Radare to analyze it. And for that, there is this AAA command which will do the basic analysis. Because the binary is small, the analysis is already done. And now by typing AFL, we can see all the functions present in the binary. We are interested in looking for challenge 1 and it is present at CC4. Now, the interesting thing is in the program counter, you can see that the crash is being originated from this offset exactly. So definitely this is something coming because we haven't solved the challenge 1 yet. So let's go to this offset CC4 and see the disassembly of the function. Over here we can see the disassembly. So all the arguments and the stack variables are being displayed here just like in any other disassembler, and the disassembly is being shown here. Now here we can see that there is this move instruction which is storing this 0x1337 into x0 register. So this is our pointer where we need to store our value 1337, and here is the comparison which is being made. So if the value at this pointer is 1337, which is 0x539 in hexadecimal, then it will go to this path, otherwise it will go to that path. Let's go back to our script and see how we can solve this. So I'm going to create a function over here with the name, let's say challenge1, and we can pass one argument QL so that we can access our QL object inside this function. Now our goal is to write 1337 at address 0x1337 in memory, right? But memory needs to be mapped before it can be accessed. So for that we are going to use map method of Qiling memory API using ql.mem.map, and it will create a memory region at specified location. This location we can pass as first argument, and one more thing, that this memory region needs to be mapped in such a way that our 0x1337 address will fall under this region. So we can have our memory region of size 1000 starting at 0x1000 all the way till 0x2000. Okay, so under size we can pass 1000. Now our memory is mapped and we can write our data within this memory range. Now we can write into this memory region using write method of memory API ql.mem.write, and this will take two arguments. First one is the address and second one is the data. So we need to write 1337 at address 0x1337, right? But one thing to note here is that we can't directly pass our value as the argument because the memory write API expects data to be in byte format. So we need to convert it using ql.pack. Now, since it's 1337 integer value, we can actually use short integer for it. So pack 16, which is the size of bits required to store short data type, and then S to tell that it's a signed bit. And here we can pass 1337. So this will convert this 1337 integer into byte form. Then this write API will write that data into this address. Okay. And Just to see what's going on in the memory, we can print out the value at 0x1337. Now, similar to this write method, we have read method under this mem API to read data from the memory. So we are going to read our data from 0x1337 address, right? But again, since it's in the byte form, we need to convert it into human readable form. And for that, we can use ql.unpack16s and then our data. Let's simply call this method and pass our ql object and see how it goes. Python 3 emulate memory read missing one position argument size. Okay. So this read method actually take two arguments. First one is the address, second one is the size. So the size, let's pass it as 2. We run it now. We can see that our challenge 1 is solved. Okay, so let's now move on to our challenge 2. The description of the challenge 2, it says make the unames syscall return the correct values. So currently, just by looking at the description, we can't get much idea. So let's move on to the disassemble code in Radare, and in the function list we can see that challenge 2 is present at this offset. And so let's see, go over to that offset and see the disassemble code. Here we do have the arguments. Then just by quickly going through the disassemble code, we can see that uname system call is being called here. Then a comparison is being made. So if you know uname returns integer value, if it's 0, then it will go to this compare equal to, okay, 48, yeah. So if it's 0, then it will go to this block, and if it's something else, then it will execute this particular block, which is the error block. Okay, moving on, here in this block, some strings are being processed, and then we have the string length function. Again, some comparison is being made, and then finally it will return. So by looking at the disassembly, I am not sure what it is doing. So let's try to see the decompiled code, which will give us more clear idea. So we can see the decompiled code using pdg command. So I have already installed R2 Ghidra. So my Radare is using the Ghidra decompiler. You can also install it simply by using R2pm-ci R2 Ghidra command, and it will automatically install. After that, again, uname function is being called and then some argument is being passed. So I'm not sure actually what this argument is. So let's try to see what the uname function takes. We can see the definition of the uname function in the Linux manual page. And here's the syntax of uname, and it takes structure uts name pointer buffer. Okay. And this is the description of this structure. So the structure has these fields. So this is the structure which is being passed to uname. Then over here it is assigning that killing string to this variable and challenge start to this variable. Then it's executing a for loop, two for loops actually, okay, and calling string length function on stack 40. Stack 40 is this one. So it's actually calculating the length of killing OS string and iterating over this string and then doing some comparison, right? Similarly, in the second for loop, it's again calculating the string length of useStack24, and this useStack24 is the challenge start string. So again, it is iterating over this challenge start string and doing some comparison. Then finally, it's calculating the string length of stack 40, and again our stack 40 is killing OS. And then if useStack 448 equal to uvar2, which is the length of our killing OS string, and it's doing another comparison where if the length of killing OS is equal to useStack 24, which is challenge start. And if this condition becomes true, then it's setting this flag to 1. So basically all we need to do is somehow make this if statement true, right? As the description says, make the union syscall return the correct values. We will try to figure out what the uname system call is returning, and we'll try to return correct values to make these conditions true, right? So first of all, the easiest way to go about it is simply hook this uname system call and intercept the arguments being passed. Let's jump to the script again and create a function with name challenge 2. Okay. Now in order to hook the system functions, we have set underscore syscall method in Qiling OS API. Okay, so we can use ql.os.set syscall method in order to hook to any system call. This will allow us to intercept and modify and even alter the return value, and we can also replace the functionality altogether. So this method takes 3 arguments. First one is the syscall name. So our system call name is uname here. Then the second argument is the callback handler. This callback handler will be triggered whenever this syscall will be executed. So let's create our callback here, challenge to callback, and we need to pass the killing object. Also, it takes second argument, which is pointer args. Now this callback handler will be passed as second argument. Then as a third argument, we can pass ql underscore intercept dot either exit, enter, or call. These are basically the different stages which tells killing when to trigger this callback, right? So since we don't want to alter the functionality of the uname function, we just want to intercept the arguments which are being passed to this system call. So we can use the exit stage. Whenever the uname system call is about to be completed, this callback will be triggered. Now this QL intercept constant is part of our killing constant. So we need to import it like this, and that's it. Then we need to define our callback handler here. First of all, let's try to resolve the arguments. In case of killing, we don't need to bother about how the function arguments are being saved into the registers or into the stack. We can simply get the parameters by calling ql.os.resolve f call params to resolve the function parameters. And here we need to pass a JSON object, right, which tells how many function arguments are there and what are their types. So as of now, we are just interested in one argument, and that is our pointer buffer, and that is of type pointer, right? So we need to tell it the data type. And again, this pointer constant we need to import, which is a part of Qiling OS constants. So from Qiling OS constant, we need to import our pointer. Fine. And this function called params returns us the JSON object. So let's store that in params variable. Now this argument will be returned back into this params object along with the value. So let's try to simply print this params. Let's call our challenge2 function and see what we get in the output. Python 3 emulate. Okay, so this is a parameter which we have intercepted just now, and it is the address which is showing here as integer value. Now we have the address of the structure. Next, let's try to read the first field of this structure. And in order to do so, we can use our memory read API of Qiling Framework. So let's get the buffer pointer into a variable. Struct address is equals to param, and we can access this field like this. So this is the address where our structure is stored in memory. Then in order to read, we can use the memory API read function. This will take first argument as address, and then we need to tell how many bytes we need to read. So currently we don't know actually what is the size of these fields. So what we can do, it says the UTR name structure is defined in UTS name.header file. So let's see the code of this using UTS name.h Google sources. And here's the first link. It will tell you that the size of each field is sys underscore nmln, and which is defined here as 65. So this is the maximum length of any field in this structure. We can read the first 65 bytes of the structure starting from this address, and this will be our system name. So let's store it in sysname. Similarly, we can read other fields as well. So let's say you want to read the operating system version field here, which is present at 0, 1, 2, third position. So what we can do, version is equals to ql.mem.read, and this will actually start from our structure address, plus we need to reach to this address which is present at 65 times of 3. So we can get it like this, and then again the 65 bytes. So this would be our version. Let's try to print these values. Sys name and the version, and let's see what we get. Okay, so it's returning it as byte array, and we can see the 65 bytes here, and the first field which is system name is Qiling OS, and the second field which we have passed, which is version, is Qiling OS 99.0 release. Right, so that's how we can pass the structure from the memory using Qiling emulation. Now we need to make this condition true. Till now we know that the first comparison is being made between the Qiling OS length and from the first field of our structure, which is this name, right? But we are not sure what this second comparison is and between which fields it is being made, but it's comparing this challenge start string with one of the fields from the structure, right? So we need to figure out somehow what that field is. Now to do so, we see over here that it's comparing the length of our challenge start string with ustack 444. And if we see here, this ustack 444 is being incremented here, and here some comparison is being done between AC stack 237 with our challenge start string, right? So the best guess would be if we somehow figure out what this AC stack 237 variable is, we might get some idea about which field it is. So let's go back to our script, and now we can make use of our stack pointer because this variable is present on the stack at 237 offset starting from the stack pointer. So to do so, we can use ql.architecture.registers.stack pointer plus 237, which if we convert it to hexadecimal would be ed. So if we try to read this address and to read the memory, we know we have this read method from memory API and then this address, and we already know that the size of all the fields are 65. So let's try to print this and see what we get here. All right, Qiling OS. Then this is the version field which we have printed earlier, but this is the field. This is our ustack 237 variable, and it contains Qiling OS 99.0 release. So this gives us slight idea that this might be the version field itself. Now, all we need to do is modify this version field in the structure to challenge start string this instead of this string, right? So we can use write method of our memory API ql.mem.write. We need to write it at this address because that's where our version field present, and we need to write it as write it in byte format. Challenge start. So that's it, and we need to terminate it with null, and our check should be bypassed. So if we run it again, yep, our challenge 2 is solved. Thanks for watching this video, and don't forget to subscribe to this channel as we will be solving rest of the challenges in the next video.